All right, let's look at another one. And you'll see the similarities here. So here we go. This is problem 316. You are constructing a cardboard box with the dimensions um, from a piece of cardboard with dimensions 2 meters by 4 meters. You do that by cutting equal size squares from each corner so that you fold up the edges. So you can see the picture there. These little corners right here are what's going to get cut out, and so those will be gone. And so we're going to uh, want to ask ourselves how big should the corners be in order for us to get the box with the maximum volume. And just like we did before, depending on the size of your uh, of your the corners you cut out, you could get a box that is, very like a pizza box, right? That is low and big, right? If you only cut out, and that's going to have a certain volume. Or you could get a regular size box, right? Kind of your average plain box. Or you could get one if you cut out lots of the corners, you might get a box that is very tall, right? So those are the different shapes you can get of boxes. We want the one that gives us the largest volume. So we would imagine to ourselves, okay, so as you approach these problems, the first thing you want to do is you read through the problem, might draw a picture like we've got here, but you want to look for what it is they want you to maximize or minimize. In this case, they want you to maximize the volume, find the largest volume. So that tells you need a formula for volume. All right. Okay, so that's the clue. You want to find a formula for volume. So for this particular case, when we take this box and we cut out these corners, let's just use this middle one as an example. The height of the box will be x as you fold up those edges. This side will be 4 minus 2x because you started with 4 and you took out 2x's, and then this side in a similar way will be 2 minus 2x. And so if you've got those three dimensions, you can now write a formula for the volume. Looks like that. All right. And so once we have that formula, let's just do a little algebra because we know that's the formula we want to maximize. So I'm going to go ahead and multiply it out. It's going to be easier to differentiate when it is in factored form, or when it is in polynomial form, I should say. And so that's going to be x cubed minus 12x squared plus 8x, assuming we did all the math correct there. All right, so that's our formula for the volume. And so that's what we want to maximize. So we know what that means. We're going to find the derivative. And set it equal to 0 to find the critical points, right? Probably on this one I'm going to divide everything by 4. Maybe that'll make my life a little easier as my first step of solving the equation. Now this particular quadratic is not factorable, so we have to solve it using the quadratic formula. And so its solutions are going to be negative b plus or minus square root of b squared minus 4ac over 2a. So running that through, 36 minus 24 is 12 over 6. And so that's going to be let's just pencil that in, right? That's going to be a 2 square root of 3. That's what square root of 12 is. And so when I cancel the 2 out of everything, I get 3 plus or minus square root of 3 over 3. And there's my answers, of course. Both of those answers, they represent minimums and maximums. And we've got to figure out which one is a minimum and which one is a maximum, right? So those are our two values right there. So to figure out if they're maximums or minimums, probably the best thing to do is to use the second derivative test. So the second derivative would be 24x minus 24, right? And so, or I'll just put it here just like this. There's our second derivative. And of course, remember how the second derivative test works. You plug in your critical point, 1.58, and you plug that into the second derivative, and you see what you get. And when we plug in 1.58, I'm getting a 13.92. What we care about is that it is positive. We care that the derivative is, or the second derivative is positive, thus indicating that we are concave up. And the second derivative test implies that this is a minimum, right? Whereas if I go in here and plug in the 0.423, I get, I'm going to get a negative value out. I guess I don't really care what the value is, but I am going to get a negative value out. So that indicates concave down, which of course implies that's where your maximum will be. So we'll get a maximum when x is 0.423. If we want to know what that maximum is, we plug 0.423 into our original function, right? So 4 times 0.423 cubed minus 12 times 4.423 squared plus 8 times 0.423. And that will equal 1.5, what's it called, 54. And these were in meters, so this is a volume, so this is cubic meters. So we get a maximum when the size of the corner that we cut out is 0.423. And what is the maximum? 1.54. That's the biggest volume of box that we can get under these circumstances.